who have lived on and cared for these lands since time immemorial. So good afternoon, everyone. If this is a first SSRIA event for you, I am Pamela Gertson, and I'm Executive Director of the Smart Sustainable Resilient Infrastructure Association, or also known as SSRIA. And we are a not-for-profit organization that is taking a collaborative approach to reducing carbon in the built environment by accelerating the adoption of innovative low-carbon solutions. We also we're an industry association, so it's very much so an industry-led approach as well. We are currently funding 16 demonstration projects across Alberta and actively sharing the results of those projects through webinars like what's being presented today, and through the Building Innovation Reference Center, which is a searchable online database of information that's related to the demonstration projects, and information of everything from planning and design documents to energy models and to final results. So which will be starting to come through soon enough, as some of our projects are starting to wrap up in the next, I'd say, 6 months. So,
exciting days.
Yeah, absolutely. This event today will likely be our last event of this year, this 2022. However, we are planning an in-person member appreciation networking event in January. So definitely stay tuned for the details on that. And if you have any further questions about SSRIA, you can certainly feel free to send me a direct message in the chat or send me an email, which I can put that in the chat as well. So depending on when you jumped in, but as I was mentioning earlier, we have been hearing a lot about retrofits and deep energy retrofits, and just this sheer size and challenge ahead of us to get all buildings to net zero by 2050. I believe the number in Calgary and Edmonton alone is close to 1 million residential buildings that will need to be retrofitted to meet those targets. And so the project is really an important step in addressing that challenge, looking out 3 different approaches to deep energy retrofits with a specific goal of being able to electrify the homes within the constraints of a 100 amp servicing. So we're really thrilled to have 4 elements working on this project with a team of really great collaborators who together bring building expertise to really a whole new level. So our speaker today, Tyler Hermanson, and then there's really a silly amount of letters after his name, is the owner and senior consultant at 4 Elements, and is an architectural technologist, an energy advisor with 15 years of experience, and a trainer for EnerGuide energy advisors. Tyler was extensively involved in the development of Built Green, Lead for Homes, and the CHBA Net Zero Energy Labeling Program. So a ton of knowledge and expertise that he's going to share with us today related to this project that we're supporting. So take it away, Tyler.
Awesome. Thanks, Pam. Welcome, everybody. Thanks for joining us. And so what we're talking about today, deep energy retrofits, obviously, as to Pam's introduction. What I wanted to do is just lay the groundwork really quickly on deep energy retrofits and what the context is we're talking about, and the general steps that a deep energy retrofit goes through. Then we're going to talk a little bit more about how these particular case study homes are going through the process, and then focus mostly on what we've learned so far in the process. So put some context there. All homes need to be renovated, right? They age, materials break down. We are constantly maintaining and tweaking the homes that we live in, and some of that is done manual, is maintenance we do every year, washing things and that kind of thing, fixing damage, things like that. And then over time we do renovation stage, right? Something, a bathroom needs to be renovated because it's out of style or something like that. And these tend to be small pieces, usually interior, to fix something that's at end of life. And for a long time, we've talked about retrofits, when you had to retrofit a building. And that's like a major overhaul, where you're looking at major infrastructure systems of the house, your whole heating system, your whole plumbing system. We retrofitted electrical runs for homes from knob and tube when we started running actual electrical grounded wires and things like that. So those were larger renovations, and often were part of what we would traditionally call a gut rehab, where you really take the house down to its studs, fix all of its systems, put it back together in what feels like a brand new house. And then in the last few years, we started to talk more and more about deep energy retrofits, and this idea of looking at the energy efficiency of homes and doing a major infrastructure update of the energy systems within a house. And often these deep energy retrofits are not a gut rehab. The homeowners don't leave the house. We don't do very much interior work. We are focused on the envelope, those pieces of the house that define the inside from the outside. So windows, insulation, air tightness, mechanical systems, and things like this. So instead of just doing a renovation and bringing, the house up to new style, or doing a little renovation and bringing it up to today's code minimum, a deep energy retrofit is looking at that future building code, that future scenario, and taking the house all the way up to these very, very high performance levels. So we're looking into the future. 2050 and beyond is kind of what we had in mind as we worked through this process, looking ahead at the new building code, the national building code that lays out tier steps and things like that. Obviously, we're looking at some major energy savings pieces, and we looked at energy, gigajoules of energy or kilowatt hours, but we also looked at carbon, and we looked at cost. We wanted savings in all three of these elements to do the hat trick approach, right? Because we've seen renos that are very energy efficient, but they actually cost more to operate, and we needed to try to dodge that. And we see projects that save a lot of energy, but they're actually still quite carbon intensive. There's a lot of carbon emissions from that house. So how do we balance that? A perfect deep energy retrofit solution in our mind is something that could hit all three targets. Comfort was something that was really important to the homeowners we were interviewing, and this conversation about energy efficiency, right? It's not just about the dollars and bills at the end of the month. We wanted a house, all of our homeowners wanted homes that were substantially more comfortable, quiet, thermally comfortable, because we were tired of living in 1950s vintage houses with very little insulation that were cold and drafty and frost building up and things like this. So comfort comes up again and again when we talk about deep energy retrofits. And then impact on carbon. We're paying attention to embodied carbon and thinking about that in these renovations. And really what we found is that just the fact that we're saving existing homes that already have a lot of embodied carbon in them, and we're not having to rebuild and infill on that inner city lot, is just a ton of carbon. And so it really doesn't matter very much how much carbon is in our wall insulation or in our windows. We've saved so much by saving these homes. It's crazy. So those are the pieces the context that we're coming at. When we approached SSRIA with this project, we were excited to kind of showcase what a deep energy retrofit could be, take a couple risks on how we might approach a deep energy retrofit with our own homes. This is one of these case study houses is my house. Project 3 is our builder's house. We have homeowners that were willing to lay it out very publicly, as well as take some risks with the envelope and some approaches to construction that we just don't see very often, and document everything. So to really watch what happens and how it actually works in the field, and take the lessons learned and provide all that information to SSRIA, the post, and for other people to use as they kind of take this ball forward. Obviously, this is just 3 homes, and we're not going to save the world with just 3 homes, but the information that we generate, we hope is going to have a long, long life. So when we talk about a deep energy retrofit, we always kept coming back to the idea of house as a system, and making sure that things fit together properly. You're messing around with the envelope a lot when you do a deep energy retrofit, and water, air, and vapor is being affected, how it moves through the house, and we're affecting homeowners and how they live in the house. One of the pieces we also wanted to look at here is make sure these renovations interact well with homeowners, and in most cases, they stay in the house through the whole renovation. That makes it a lot more possible to do 1 million home renovations if families don't have to move out for 6 months. So with that house as a system approach, kind of the first topic we talked about with homeowners and were part of our planning was the envelope. All the homes had a lot of heat loss through air leakage, so we had to have air tightness. Whenever you add air tightness to a house, you need to look at ventilation. And so we've been paying attention to air quality, radon levels, and adding ventilation systems to these homes for an HRV is very important. Windows are part of that envelope too. If you're going to spend all this money doing the walls, you're going to want to look at the windows at the same time as they interface with that wall insulation, they interface with water tightness and all these important things. So this is a big piece of what we're looking at. Then we're also looking at mechanical systems that provide heating and hot water to these homes. We've drastically reduced the loads that these homes have. Project one, started with a 15 kilowatt heating load to keep that house warm in the middle of winter. By the time we're done, it'll be under 5 kilowatts. Well, that makes a big difference in how a house needs to operate and what kind of mechanical systems make sense. So we're looking at heat pump technology. We're looking at very energy efficient mechanical systems, or at the very least planning for the adoption of these very energy efficient heating systems. We'll talk about that. And electrification is on the radar here, right? Because we know that to get to a full zero carbon scenario in the future, you're going to be running off renewable energy in the future, probably to a grand extent. And there's lots of conversation about electrification. And we wanted to have some case study homes that really dug into that, see how that's going to work, see what's practical and what roadblocks you run into. And the kind of icing on the cake or the final piece of the deep energy retrofits is the solar panel systems that go on the roof. This is a huge part in Alberta about how you decarbonize your home's emissions, because our electrical grid is still so carbon intensive. And so solar became a big part of how you lowered the carbon intensity of your house in operation. But that we ran into lots of challenges with solar because we're inner city existing homes. So we'll kind of talk about how that piece fits in as well. But these are the kind of the big ticket items. You look at it in deep energy retrofit. You're talking envelope, you're talking mechanical, and you're talking renewable energy. So we have 3 houses in our case study project. Project one is a 2-story with a walkout basement, secondary suite. This is our home here, and my family's owned it since 2000. My dad and I renovated it in 99, 2000. I remember standing on top of a ladder, snapping off shingles, asbestos shingles, it turned out later. Dad's like, "Oh, just turn your head, don't breathe it in." Or shoveling out insulation in the attic and this kind of thing. So we've been renovating this house for a long time, making changes. And the last renovation we did was in 2014, and we put a new basement and gutted the basement down to studs, a gut reno of the basement, and put a new mechanical system in. Focus on energy efficiency, and we knew we were going to do the rest of the deep energy retrofit later, but we only had the budget at the time to do the basement. So we've been doing this deep energy retrofit from the bottom up, really starting with the basement and working our way up. And we'll talk about how maybe that isn't the best approach for a lot of houses. This project is LEED registered as well. This is a LEED renovation. So we've been monitoring and following the LEED homes checklist and guidelines throughout since 2014. We started working on this. We're still LEED registered. We'll see if we can make it across the finish line this time. Original house built in 1954. Actually built just down the road in a factory in 54. There was a manufactured home manufacturer there that did it in the winter when they weren't busy on other projects, and they would just drive it up the hill, park it here on the lot. And so we're heated by a 96% efficient condensing boiler that also does the domestic heat for both the secondary suite in the basement and the residence upstairs. But we had a really terrible envelope upstairs. We had R11 walls only because we added our 7.5 in 2000. These walls were uninsulated originally. And a little bit insulation in the attic, vaulted when we added a second floor. Basement's pretty well insulated. We had extra insulation when we did that and some exterior insulation, but our air change was terrible. surprisingly bad, actually. I knew we had tested this house various times, kind of half tested it or looked for leakage and fixed things as we were renovating the basement or such. But we've never actually done a full envelope CGSB 149 full envelope test, right? Because shoemakers' children go without shoes. Turns out it's way worse than I thought. 8 air changes, one of the worst houses we've tested. We've got a complex set of geometry, and we had some very big areas that my dad and I had renovated without a real focus on air tightness back in '99. And so now's our chance to fix that. We use 133 gigajoules or so of energy a year. Most of that is going to space heating, very typical of a house of this vintage. So we're a ways away from net zero, and not terribly far away from code minimum. You know, obviously we've made improvements. So when you look at our kind of checklist of things we would do if assess if this was a good house to do a deep energy retrofit, we're not a bad fit. We're not the best fit. This house is on a sloping lot. It's got a walkout and a sloping backyard, and it's taller, right? We have a 3-story section on one side, and that adds considerable challenge to renovating this house. It makes it less of a perfect fit for a deep energy retrofit. We did have some older vinyl siding, but it wasn't at end of life. It didn't need to be replaced yet. And we've got a complex roof with concrete roof tiles. That made the renovation much harder. So that was a strike against us and being a good fit for a deep energy retrofit. We had lots of room on our side yards. That's an important factor. And things looked really good from a structural standpoint or a water intrusion standpoint. We'd already dealt with asbestos in the house and weren't planning to disturb anything or didn't have to do any remediation here. So, you know, 5 out of 10 maybe for fit on a deep energy retrofit. Project 2, just built on the other side of Confederation Park from us, 1954, so just a tiny bit newer. This house had upgraded its furnace and hot water tank just as equipment aged out. Not that too long ago, but the envelope was still original. R11 again. This one had batt in the walls, but not very much. Poorly insulated basement and still quite a high air change rate. An old fireplace had been retrofit in the 70s or 80s and was quite leaky, quite uninsulated. Lots of old, poorly sealed ceiling penetrations and things like that. Very common split level style house. You see lots of these in Calgary. 134 gigajoules. So even though this house is actually a little bit bigger, very similar amount of energy. It's using energy a little bit differently, less to air leakage, more to envelope, a little bit more to basement, that kind of thing. Because our house had been renovated in the basement at least already. So just coincidence that it happens to be about the same energy at the starting point. This house was a better fit on our viability checklist in hindsight. It's a good sized lot, good age of house, nice simple shape, nice aging exterior that needed work, a roof that definitely had to come off. That was the main motivator, to start this. Oh, we need a new roof. Well, we're going to do a new roof. We should do solar panels. Well, if we're doing solar panels, we should do energy efficiency, right? And you can see how the decisions work their way down, and that's very common. And we had a good structural base with this house as well. Nice solid framing, solid basement, or so we thought. A few hazards, or so we thought. That investigation becomes really important as you're planning out a deep energy retrofit. We'll talk about that. Project 3 is a 1955 bungalow, also nearby. All of our houses were just a short drive away from each other, which made this project much easier. This house had also been renovated previous generations. The basement had been suited out previously and finished. Windows had been swapped out previous years. Interior was fully renovated. And so again, you had some work had already happened, right? But we had an older furnace that was ready to go, older hot water tank that was ready to go, and still an quite original envelope. Few changes there over the years. So lots of good opportunity here for energy efficiency. Surprisingly, one of the tighter homes, 5.4 air changes. during the initial blower door. This house used the most energy. It's a bungalow shape, so for its square footage, it has more surface area. It had a very poorly insulated ceiling, an extra area there, so that really pumped up its heat loss. And then an inefficient set of equipment that hadn't been upgraded recently was driving that increased energy consumption as well. So this house, showed worse on the EnerGuide label and ticked all the boxes for being a good fit on the deep energy retrofit kind of viability list. 10 out of 10. This is a great, easy candidate to deep energy retrofit. So when we picked these houses as a set, we had a nice spread between a house that is going to be super hard to deep energy retrofit, and maybe, Tyler, you shouldn't do that, all the way to a house it's like a perfect, if we could do this all day long, it would be great. Bungalow, square, nice. So that really helps us is going to help us when we now analyze the costs, right? Because we have the cost per square foot and the cost per units on a really complex house with a complicated lot, and then a nice easy bungalow. And we're going to start to see what the spread is. So all these homes are still in mid-swing, envelopes being finished, insulation. We're kind of getting to what we'd call lock-up stage or envelope complete. Siding and cladding is a little further down the road, hopefully next month. And then finishing details and trim will probably trickle into the new year. We faced a lot of delays in getting these houses off the ground. Windows, mechanical systems, just coordinating in a very busy construction season post-COVID. Terrible time to try to do a renovation, just in general. Ask any builder, and we got caught up in that as well. But good lessons learned there too. The wall approaches are very different for each house, and that was important to our project. So we're getting a diverse set of details, a diverse set of approaches, see how these things work. So project 1 is using 4 inches of the new generation XPS insulation, R5 per inch. Usually we never would have recommended XPS insulation because the embodied carbon of the blowing agents were so bad. The original 1.5 inch insulation we added at 99 when we weren't really paying attention to embodied carbon has just barely started to pay off its carbon debt because it was so bad back then. The new generation blowing agents are like a factor of 10 or more reduced in embodied carbon. So we felt more comfortable using this approach. And it gave us the ability to do a face sealed air barrier. So in this case, a tape seal finishes the house. I'll go into detail here. So from a detail standpoint, to go over a variety of assemblies and a variety of wall planes, having a monolithic air barrier insulation material was an advantage for us, and was something we wanted to keep. We also kept the original 1.5 inch. We found, it doesn't make any sense to take off any insulation you can possibly keep because you're just working against yourself. And we want to, because this should be the last envelope. This is an R30 some odd wall. When we're all said and done, should never need more insulation. So we can put a nice long-lasting cladding on this and never have to take it off. It's just maintain and clean from here on in. So making that step up to a kind of a long-lasting durable siding was important to us. We were glad not to have to put vinyl back on and be on a 10-year vinyl cycle. So you frame out the windows with kind of a buck extension, and then the insulation ties nicely into that. And then the tape seal provides your air barrier across the whole face. This allowed us to use the foam as a chase where needed for new electrical. This is a great opportunity to add new plugs to the 1955 Ford house that had very few interior plugs. It's a great opportunity to rough in for a future EV charger and solar panels. And this thick wall allowed us to quickly run stuff around. It is a lot of tape. You realize just how many seams there are, how many little details have to be taped up. Project 2 is going with a super thick EFIS product, so exterior insulated finish system. So acrylic stucco on top of thick EPS insulation that's adhered to a liquid applied air barrier that goes across the whole envelope. So in this case, you have to take everything off the house. You got to go right back down to original sheeting, and then apply a liquid applied air barrier that kind of is a nice way to physically seal up everything, because it goes right across the sheeting, right from outside. These simple homes don't have a lot of transition and corners and stuff, so an exterior air barrier makes a lot of sense and provides a good water protection as well. When the insulation goes on, sits on a drainage plane, and then gets that acrylic finish, acrylic caulking, or acrylic stucco finish across. This house, we also had a poorly insulated foundation originally, and because it was a shallow basement and a crawl space on one side, it was a great opportunity to insulate the basement. So we went with a hydrovac approach, where a hydrovac truck came in, sucked out a little trough around the whole house, inspected the concrete, everything looked good, and we could slot in R20 exterior insulation and protect that foundation, and then just very easily fill it back in. So we didn't have to disturb very much. There wasn't a big pile of backfill around, and this gets tied into the envelope as we go around. So windows are just starting to go in, just went in last week, kind of a quick seal with spray foam, and then they'll get taped and caulked into the envelope as we go around the house, as we finish. Project 3 kind of probably has our most innovative approach that we had the least examples of. And this was a double wall exterior strap. So you might call it a Larson truss wall, double wall. So what we did is fabricated a bunch of kind of mini wall trusses with plywood that holds the two layers of framing apart, and then reframed the house around. And you see, we didn't put a barrier against the sheeting. There's no poly there. We didn't put a new house wrap in, because we're moving the whole plane of air tightness and everything to the new face of house wrap. So this whole cavity is really the same insulated cavity as the back wall that's behind it. The air barrier is going to be on the outside. The vapor barrier is on the inside. And so this lets us use a very inexpensive blown cellulose insulation to very high R values. This is the best insulated house out of the set, because blown cellulose is so cheap. You might as well use lots of it. There really isn't a cost penalty between 8 inches or 12 inches. You just pick whatever thickness you're comfortable with, because it's almost the same cost. This gives us nice deep exterior window ledges that you kind of frame out with plywood bucks. Waterproofing becomes super important here. And how you tie this up to the top of the roof was really important. We had to transition from this now outset 10-inch wall face, bring that air barrier back across to the original ceiling work that was done in the attic. And so to bridge that and look at those transitions, what we did was actually close off the original rafter ventilation, spray foam that top of wall, really encase that top plate of the framing to make sure there was no thermal bridge there that was going to cause a condensation risk or be our weak link in the thermal envelope. And then you say, oh my God, there's no roof vent. We talked with codes officials at City of Calgary. They were fine with us just moving roof vents up the new insulation level. So the attic was filled with quite a bit of insulation, and we just put roof vents at the low side of the north end of the roof, and then ridge venting at the high end. And the building code was happy with that. We have lots of low ventilation coming in. We have still a high stack effect pulling air out the top. And we should have all the ventilation we need in that attic still, even though the very bottom rafter edge is not ventilated. There is a patch there that doesn't get clear space, and that was approved. So this let us do a good thermal bridge here, thermal protection, and nice transition detail. So when you start to compare these wall systems, the jury is out. I think as we finish up here and we kind of get out of the rush that we're in right now, we want to sit down and as a group just sit down and say, okay, how did all that work? What was the cost per square foot? What was the hours to install? How do we feel about these three different approaches? They all have their benefits and drawbacks. And I was going to say which one I thought was the easiest, but it's almost too early to say. Until I sit down and we talk with everybody, I didn't have a clear winner on ease of install. Definitely the XPS is the thinnest wall in our system. So if you were tight to a side yard, the XPS is just really densely insulated at 5 per inch, 5 and a bit per inch. So kind of wins in that category. Cost, I also hummed and hawed a little bit. We haven't done our final numbers yet. I have my instinct on what's the cheapest one, and certainly know the cheapest one per R value. But it'll be interesting to see how it compares when we look at the final numbers. One thing we've noticed already is that the cellulose wall is the quietest. A noticeable change in kind of acoustics in the house once that was buttoned up, because really there's no thermal bridges, there's no screws, there's no strapping. And you've got this nice thick wrap of insulation that goes around the house. And so it got substantially quieter when this wrap was done. So, that's an interesting takeaway. I'm going to talk about the mechanical system approaches quickly, and we can certainly answer questions as we get into the Q&A part. We're not done on the mechanical side. I think it's too early to say too much. Both of the heat pumps aren't fully commissioned yet. The project 2 is still kind of in the throes of an interior renovation, and we really don't know how the heat pump hot water tank is working fully yet. And the interesting that happened, project 1, my house, ran out of money the first, and I had the newest equipment already. My boiler was only a few years old. So it was really too early to go all electric, too early for me to swap out my boiler. So we decided to stick with natural gas, stick with our boiler, and just rough in for electrification. So I put a new electrical panel on the outside of my house, ran the electrical lines that I would need to run a full electric heat pump based system, or even a boiler in the future. We upgraded our service, we'll talk about as well. So I'm ready to electrify. As soon as Daikin brings the air source heat pump over from Europe that I want, maybe we can talk. But at the end of the day, we decided to pull back a bit and couldn't take ours all the way to net zero, and didn't put heat pumps in our house. We still think we're ready for it. Project 2 and Project 3 were ready to go full net zero. They were ready to electrify and get rid of that gas line because we had made them so efficient. They weren't using very much gas in the model anyway. And we had the roof area for solar. So both houses are going with an integrated heat pump hot water tank. So you're taking a bit of heat from inside the house, you pump that into the water. Because when you think about it, 6 months of the year, there's kind of extra heat in the house, right? We're in summer, there's lots of heat there that you could pump into your hot water very efficiently, and you get that annual efficient. In the winter, yes, you are increasing your heating load slightly, and it pumps out a little bit cooler air. So it's important that in the mechanical room that these sit, you have a source of warm air to stop that room from getting overly chilled, and that you have a plan to keep that air warm. You wouldn't want to put one right next to your couch. It would be a cool draft. And we're noticing they are louder than your typical tank experience. So they need to be in a mechanical room with a door and that kind of thing, because there's a mechanical noise there that a normal tank doesn't have to the same level. And then both these systems went with an air source heat pump. So cold climate air source heat pump works in the summer for air conditioning, works in the winter for heating down to about -25 or so, and still has very high efficiencies at those levels. You're losing capacity, but these homes don't need very much heat in the first place, so that still has all the capacity the house needs. And if it gets really cold and it goes below that -25, which is actually pretty rare in Alberta, we don't spend a lot of hours below -25, although it feels like eternity. There's a backup resistant heat, so it can turn on 100% electric heat to top these houses up. So that's the quick overview of these houses. I'm going to flash through some of my lessons learned, and then I'll turn it over to questions and we can discuss a bit. I think one thing that we kept saying early on in the evaluation too, and we kept coming back to during the renos is, if you're going to touch something, you better make it right, bring it all the way up to what you need for 2050, so you never have to come back and touch it again. Because it was so frustrating to go to stuff that I had renovated in 99 or I had renovated in 2013 and be like, gee, Ty, you missed that detail. That could have been better. You've got to undo this work and do it better this time. And so when we started to run out of budget and you're humming and hawing about whether you should do solar panels or do the roof or not, you had to be really careful, right? Because the temptation was to save your budget and undercut something like insulation thickness and say, well, I'll add more insulation later or something. And the numbers and the discussions, that doesn't make sense. Do what you can properly, fully, and then be done. If you can't do it right, then don't do it at all. So we ended up leaving the roof tiles on our roof. It was just a few $100s for us to buy some extra tiles to fill in our roof extension that we needed to cover the wall insulation. And we could leave that roof in place for another 10, 15 years. And at that point, we'll be able to decide, let's go full solar. Let's put the solar on the right sides of the house and maximize things and make some choices then. Rather than have to remove solar panels and undo work that we just did this year and that kind of thing. So you're really thinking carefully about transitions because you're going to have to break this up. These renovations are surprisingly complex. I think we knew that going in, but we didn't fully appreciate just how complex. Part of that complexity comes from just having so many little scopes of work, right? I needed an electrician for 2 hours. I needed a plumber for a minute just to cap a gas line. Well, that's really expensive to call a trade in for such small pieces of work. And that's a timing point that has to be coordinated and you have to get things in the right order. So that becomes a real challenge. And a lot of the scopes of work would normally be done by a trade, a soffit and fascia guy or a roofing guy or an insulator cider kind of guy. In a lot of cases, the scope of work was so small for some of this work that it was awesome to have kind of a jack of all trades builder that could do a lot of this stuff themselves. Because it was really important to try to limit the amount of hands involved and try to coordinate that complexity. So if you can cut a piece of flashing yourself and not have to call in an eaves trough guy, that's a huge advantage. If you can do insulation and siding yourself, not have to break that up between two trades, that's a really good advantage. And have to be really efficient with your electrical plumbing type scopes of work. Supply chain, huge problem for everybody in the construction industry, and we were no different. Windows were taking 20 weeks for delivery. We're still waiting 3 months for a meter swap from NMAX. Like that's not normal turnaround times, and that made it really hard to schedule the rest of the work. You can't finish the insulation exterior air barrier if the existing meter is still stuck there waiting for an NMAX disconnect, and so a bunch of scope kind of gets stalled out and you have to juggle these. So some of these problems are just welcome to 2022. They will naturally work their way out. But these types of renos are always going to be complex. I think that's something we have to acknowledge and appreciate. Transitions, planning out how you move from one type of construction to another, one age of house to another, or one phase of a deep energy retrofit to a future phase of the retrofit is super important. We initially went into this planned out for a one-shot deep energy retrofit, right? Like we're going to do it right, we're going to do it all, and it'll be done. Budgets come in, prices increased. You can't do it in one step. And so now you got to put some extra thought into how you're going to plan for that next step, because you don't want to paint yourself into a corner. You don't want to have to undo a bunch of work in the future when you come back to do the next step. So making sure you've got the right transition of air barrier, that there is a tab for you to tape and seal into later, or spray foam for you to connect into later, or something on your window details that allows you to swap something out later. Roughing in for a future penetration for a mechanical system, all these types of things to make it easier for the future. So, we ran conduit for what we were going to need for the heat pump in the future. We planned where the heat pump was going to go in the future and make sure we had a path for the line set to come into the house that wasn't going to require us to tear apart all the siding again and these types of things, right? So there's a bunch of things that you kind of put on your planning list depending on where you at in your scale. And solar is one of those things you probably often phase out. Either it should be the very first thing you do, will often be the last thing you do. And so make sure you don't have to tear the house apart to get the solar wires and stuff in is important. Another lesson learned, it looks like a terrible siding, but it's actually a video. The little details of air sealing are so important. You're going with different air barrier materials, and the details are a little bit complicated. So doing a really thorough check of the homes before you start to clad is super important. We did this walkthrough just a few weeks ago with the blower doors running and found some surprising leaks that we weren't expecting. We were able to get on top of them before the siding went on and make sure everything was coming together the way it should. And you have to be careful with these retrofits because you are moving that vapor breathability line, and a small air leak in a bad spot could cause you problems in the future. So we need the envelope to be nice and tight. And so you can't wait until everything's sided and you've covered over your air barrier to find out if you've got some weak spots. You need to thoroughly check early on and make sure to catch all those details and spot check before you get all the way down to final. So we're gonna have to test again. This wasn't the final blower door, but I think it's really valuable. That is my main form of content. Hope you found that interesting. But I hope there are also some questions and we can have a little bit of debate now too. So I'll turn it back to you guys.
Thank you so much, Tyler.
It's crash course. That's a lot of information to throw at you in 40 minutes.
Yeah, but I think you really really highlighted the reason and the purpose behind having this type of demonstration project is because even with you and your team who has so much expertise and just so much knowledge in this area, you're still learning, going through this process and identifying those complexities. So it definitely, yeah, it highlights, partly I'm listening, I'm like, oh my God, how are we going to have the solution to this? But it's in starting to really understand all the barriers is what we need to do to get
the 4th and the 5th deep energy retrofit will be much easier. The 10th and the 12th and the 15th, we're on a good track.
So I'll invite everyone to, if you have questions, to throw them in the chat. You're also more than welcome to unmute yourself and ask. So maybe to, for me to kind of manage that process, just put your hand up and then I'll call on you and you can unmute yourself and ask your question. So first up, I see Doug got to the top of the line. So I'll have Doug, you can go ahead on mute and ask your question.
Hi, can you hear me?
Yeah, go ahead, Doug.
Hi, Tyler. You had made a little mention about roof extension to cover the wall extension, just adding a few more tiles.
Mm-hmm.
Can you expand on that a little? Because that's one of the things that I've thought about, that, we add 8, 10 inches or whatever to the exterior wall. Suddenly your 18-inch overhang is now like a 10 inch or something, or 10 or 8-inch overhang. And it could potentially, I'm not sure, if I would always like the look with such a small overhang. So can you just go into a little more detail about how you might, it sounds like you may have addressed that in your case?
Yeah, I think you can just see a little bit of our roof extension here that Corey put on, because this house originally had no eave on that side. And you've touched on something really important here, Doug, that we really appreciated later on in our project, which is the roof eave is really important to durability, obviously, but also the aesthetics of the house. And as you potentially add 10 inches of insulation, you're going to change that aesthetic substantially. In most of the houses they had an 18 or a 24-inch overhang. So to lose 8 inches or 10 inches was okay. It still looked fine, and it fit. On my case, some of my elevations had no overhang already, which isn't great and was already making us worried. So this was an opportunity to fix that. And we were also only adding 4 inches. So we bumped it out just to give us a 12-inch overhang, and we thought that was a good compromise. If you go too wide, it structurally becomes challenging, and you really got to tie in the whole roof, and there's kind of structural connections you'd want to worry about and things like that. So it's a balance. So it really is part of your architectural design planning stage to look at what the new overhang is going to look like, what you want to have, and start planning that out early. And we realized that in reality, we should have planned the roof overhang more at design stage, pre-construction, than we appreciated out front.
In your case, it looks like you've got mainly gable type.
All gables.
We're cottage style, so I'm not sure how we would, if we did want sort of more of an overhang, I could see it being more of an issue trying to do it. Yeah, like for example, in that situation where.
Yeah, and I think Steve's house still has a nice
soffit down at all, because our windows are already not, our ceiling height is not that high, and so our windows, top of our windows, I don't want them any lower than they already are.
That's right. And so, Steve had to make that compromise on project 3. I think, we all think the house looks pretty good with just a 10-inch narrower overhang. There's still a nice overhang there. And the house is getting a little bit more of a modern treatment in the final finishing that I think is going to punch nicely.
Right.
If you really wanted to maintain a perfect 24-inch overhang, you're going to be stuck on some architectural styles, and it's going to be trickier for you. So you may need to lift that soffit up so it slopes with the underside of rafters, which we found 2 of the houses originally had that kind of soffit, but in the 70s, the style changed and you drop that soffit down. Well, an opportunity in a deep energy retrofit is you don't need that ventilation necessarily anymore. So open up those rafters, and that actually gives you a bit more loft above some of your windows. So you get some neat opportunities with a retrofit as well.
Okay, thank you.
Peter, you want to go next? You're going to correct. What did I get wrong, Peter? Come on.
You got nothing wrong, Tyler. I am in awe. This is wonderful. What a huge contribution to this body of knowledge that we have to generate. My question is, how quick can I get these on our case study gallery?
Well, you saw the plug for Retrofit Canada there.
Yeah, I did.
Flashed over quickly. So
Yeah,
definitely we're gonna be getting these houses onto Retrofit Canada as soon as we have finished siding. So really we're counting in weeks now, Peter. We'll be putting the case studies together and sending them your way. Because I think, and I appreciate the comment. Thank you very much. I mean, that means a lot coming from you, that we're adding to the body of knowledge here. So very excited to get the information out to people. And Retrofit Canada is going to be a big spot for information about the pictures and the story of what we've done here. And then SSRIA is going to be the location for the technical stuff, and that's really where a lot of later on in the spring you'll start to see documents and resources at SSRIA that you can download and pull from.
And I think something that you highlighted in your presentation is there is a need from the different audiences for information. So there's a fairly significant consumer education that needs to happen here. And then of course there's that workforce piece as well. So yeah, glad that there's multiple resources and how we're sharing this in different ways.
Mm-hmm.
I was just going to check if that was Peter's question, if he had a follow-up or.
Well, I confess I came in late because I was working on something on the Sundance retrofit, and I want to know if this recording will be available.
Yes, absolutely.
Great. Yeah, no, it's wonderful. Really, really inspiring.
Good. Thanks, Peter.
Andrea?
Hi there. So I have a question about your slides about like trying to classify the project as whether or not it's deep energy retrofit. And I think that information is super valuable to society, right? And understanding, like, lots of people buy buy houses and they have to decide if they're going to tear them down and put in a skiddy. It might be a net zero skinny, but if they're going to do that, or if they're going to retrofit it. And I think like that checklist, like, is immensely helpful in trying to understand that. And I guess one of my comments or question is, it would be great if it could be built out further to understand, like, what are the implications if you are a no instead of all yeses? Like, what are the downstream impacts that you have to consider?
And the only implication is that it's more expensive.
Yeah, well, but even then, like, if we could start gathering that data on, like, order of magnitude, does this double the cost, or is it 10% of the cost, or whatever?
That's why it was so important for us to do 3 projects, right? This just wasn't one, and it wasn't one identical. You know, we had 3 different approaches on 3 different types of houses, similar age, I'll grant, but different implications. So I think the cost per square foot and the cost per reno that we get will provide a little bit of variance, and we'll start to bracket what some of these costs can be, from a perfect fit to a less perfect fit. And so, yeah, that's definitely something that will come out in our milestone 3 report. So that is 6 to 8 months away, but is definitely something that is under our project here.
Yeah, and I think just like from discussions I've had personally with designers and architects, even some of the ones that profess to be sustainably focused, like, it's an argument to say, leave the house, let me leave the house, right? Like, the minute you start talking about things, they're like, are you opening to demolishing and building again? And then you hit on one little snag, and then that's the recommendation, just demolish, right? So I think that this needs to help us debunk that kind of, and empower the owner to be able to challenge those discussions, because if the architects aren't coming to the table with it all the time, the owners need to challenge it as well, right?
And it is crazy, like, if you're not super careful in how you build a net zero home, I mean, you're dumping another 30, 50, 100 tons of carbon emissions in building that net zero home. It's going to take a long time for it to pay that back. By keeping the house, even if we're adding another 5 tons of emissions in insulation or siding, that's nothing in comparison. You know, it's such a big difference.
Just as a kind of follow-up on that, there was a question in the chat regarding whether you're suggesting that the 1980 era house is the optimal kind of cutoff age for retrofits, or is it just that there's a lot of value to start retrofitting in that age group?
So the reason, and this is up for debate, it's not a magic number. The millennial break at 1980, I think, is really, construction changed substantially from 78 to 82, where you started to make the transition to fully insulated, decent vapor barrier, mechanical systems changed and that kind of thing. Whereas in the earlier homes, it was more and more common to have no insulation or very weak insulation, you know, especially in the 50s and 60s. And so we need to start there, because those houses are hemorrhaging energy. But in reality, you realize most of those 50s and 60s homes have been periodically renovated in the last 50 years. So maybe they're not as bad as we thought. We need to use the EnerGuide system to find those nuggets with 150, 200, 300 gigajoule energy consumptions. When we look at the 1980s homes, you know, they already tend to be quite a bit more efficient, and they're just coming up on kind of retrofit age, generally. So, and the approach is a little bit different, I think, with an earlier, like a 1980s home. You're going to be dealing with trusses, you're going to be dealing with OSB, you're going to have a cavity that has R12 in it or R20, and some of that has trickle down effects on how you might approach a deep energy retrofit. It gets easier, right? So these older homes are actually going to be the harder ones to retrofit in a lot of ways.
Perfect. Another question just around the approach that was used for mechanical ventilation.
So yeah, ventilation was super important to all 3 projects, because we knew we were shooting for super airtight levels. And so each home was poorly ventilated or had no ventilation system originally, and all 3 homes getting an HRV ventilation system tied to their forced air or directly run in case of project 1 to the bedroom and through the house. So definitely ventilation is part of the strategy, but it's actually not that hard. You're changing the mechanical system out, tying the HRV to do a hybrid system. At that point, it's pretty easy. Or to go through the forced air system is pretty easy. It did open up. You open up a little bit of drywall inside the house to do a good ventilation system. We had a bathroom that had no ventilation, and that's not LEED allowed in LEED. And so we had to find a way to get an HRV duct into the bathroom. Luckily, we had deadheaded some old ductwork and managed to repurpose old heating supply ductwork to become ventilation ductwork. Neat opportunity you get when you're lowering the heat load of the house to a third. You don't need all the heat ducts have. And so you get some interesting opportunities that way. But a careful ventilation plan and review is super important step as you start to tighten up these homes. But in the grand scheme of things, it wasn't a big budget line either. Compared to insulation and windows, it's kind of like a rounding error. So yeah, of course we put good ventilation in the homes, but it wasn't a big deal.
And you did touch a little bit on the embodied carbon of the XPS. And there was just a question here if embodied carbon was a consideration in kind of all the material selection, or were you really needing to aim for that operational carbon first and foremost?
We got lucky in a lot of ways because I never promised Pam that we were going to do a lot of embodied carbon work, but the ECM2 tool came out from LEAP while we were in the middle of this project. And so we quickly jumped on that and started reviewing some of our materials. We knew that we were going to be so far ahead from an embodied carbon standpoint by just keeping the deep energy retrofit house that we were in good shape. But and we knew that we had to use next generation XPS to be able to talk about XPS at all. And so Owens Corning did come on board and spot us some product to get that in use. When I look at the surprising thing when we looked at embodied carbon, and that is why project 3 went with blown cellulose and wood framing. Embodied carbon was important to them, and we really wanted to showcase a really low embodied carbon approach. But the surprising thing was the acrylic stucco, the EFIS, is actually the highest embodied carbon of the 3 homes. The acrylic stucco is actually hugely carbon intensive as a material, and so that kind of tipped their scale in the insulation envelope category, but only by 2 tons compared to the best house. So when we're talking, we save 50 tons by not tearing these houses down, 100 tons if you count rebuilding a new house in its place. And so to argue about 1 or 2 tons here or there, no big deal. Don't worry about it.
And then you did touch on, the health, the health aspect of the buildings when you start to get into some of these, into the deep energy retrofits. Have you had any feedback yet on radon or other air quality issues in the house, or is that?
So we did do radon analysis in each of the homes before the renovation. We'll do it again at the end. And we have been running a live consumer grade IAQ monitor for all the homes, and we couldn't help but watch the numbers. I think we couldn't you want to look at the data, you want to know, but all the homeowners were surprised, suspected or had confirmed radon previously, so we knew radon was going to be an issue, and they all homes spend some part of the year above 200 becquerels, so radon needs to be addressed, and air sealing the basement and removing penetrations that allow radon into the house are important, and we'll see how low they go. I think some of the surprising things were, because we assume these houses are so leaky, they must have great CO2 levels all the time, right? There's just so much fresh air blowing through the houses, and we open the windows all the time and the house is never stuffy, and that's just not a problem in our house. And then you start to run a CO2 monitor log and you realize, wow, your house hit 1,400 parts that night, and you're like, oh, I didn't sleep very well that night. It was really hot, and even my leaky house ran out of oxygen, right? It became too stuffy. And so even these older homes, we do need to pay attention to fresh air supply and ventilation distribution. because some parts of the year are just too still, too warm, and you can easily get into the 2000 parts per million and just have a stuffy, poor night's sleep. That is the biggest trigger, though. We always found a correlation, like, I didn't sleep very well last night, and you go check the monitor, like, oh yeah, it was over 1200. That's why.
Fantastic. Well, that was a really fantastic presentation, and thanks everyone too for your great questions. And I think this is probably a topic we could have a discussion alone about for an hour at least. But so yeah, we'll continue the conversation anyway down the road. We'll find other opportunities to keep batting around this deep energy retrofit and this retrofit challenge. So thanks
Stay
again.
tuned for milestone 3 coming soon.
Right, yeah. So thanks for that, Tyler, and all the great information you're putting out. And to the rest of your team, Sate and Peter and Steve. So thanks all for being here. And we'll get an email out probably next week with the recording of this video, so you can go through it again if you want.
Good. Thank you very much.
Thanks, guys.